Dear students, today in this class we shall be discussing about magnetism and matter. So here we shall be learning about the different classification of magnetic materials. That means those materials which exhibits the magnetic properties when an external electric field or magnetic field is allowed to pass through it. So what are the different properties of different classification of material that we shall be learning in this chapter? So for this is our first class on magnetism, and in this class we shall be learning about the behavior of a solenoid as a bar magnet. So whenever any current is passed through a solenoid having number of turns, it will always behave like a bar magnet. So we need to prove that through mathematical treatment that a solenoid behaves like a bar magnet. So how do we prove? Let us give a small example. Suppose this is a bar magnet. This is a bar magnet, and these are the two poles. Obviously we know one is the north pole and one is the south pole. And this line is known as the axial line or the axis of the magnet. If the pole strength, M is known as the pole strength of the given bar magnet. If M is the pole strength and you are asked to find the magnetic intensity somewhere at this point on the axis of the bar magnet, and considering the fact that the point P is very much at a large distance from the center of the bar magnet, in that particular case, we will be obtaining an equation of this form. And the equation is like this: mu naught by 4 pi 2m by r cube. A equation of this form will be is obtained generally whenever you obtain magnetic field due to a bar magnet at any point on the axis of the bar magnet. Similar to this, in this case we shall be taking a solenoid. Similar to this, we shall be taking a solenoid, and on the axis of the solenoid we shall be considering another point P. And at that point P, we shall, on obtaining the magnetic field, we will obtain an equation of this form. So if you can obtain an equation of this form, we can say that the magnetic field associated with the bar magnet and that to a solenoid are similar. So we are required to find an equation of this form related to a solenoid that carries a current. So let us begin. So let me first draw a solenoid. Let us consider this to be a solenoid, and let this be the axis of the solenoid. And this solenoid has number of turns. So like this, it has got a number of turns. And let the radius of the solenoid be smaller. And for our simplicity, we will consider that the solenoid is divided equally into two parts. That is, we consider this as the x-axis and suppose this is as the y-axis. And the length of the solenoid, whole solenoid, is suppose twice m. And let us consider this to be the origin of the solenoid. Now we are required to find the magnetic intensity at any point on the axis. So let the point be P, which is at a distance suppose r from the center O of the solenoid. We are asked to find the magnetic intensity at point P due to the current carrying solenoid, because we know whenever a current is passed through the solenoid, it will be behaving like a bar magnet, or in other words, a magnetic field will exist inside the solenoid, and if the solenoid is long, that magnetic field is almost uniform. Inside the solenoid, the magnetic field is almost uniform. So how can you determine the magnetic intensity at point P? So for that, what you have to do, you have to consider a very small element within the solenoid. Let this be a very small element of the solenoid, and let the thickness of this small element be dx. Now here we have to find out if N be the number of turns per unit length of the solenoid. That is, the solenoid that we are considering is having n number of turns per unit length. N number of turns per unit length. So what will be the number of turns in this small element? The thickness of this element is dx. So the number of turns which is included in this small element will be, therefore, number of turns of the small element of thickness. The thickness is taken to be how much? Dx. So the number of turns of the small element of thickness dx is equal to, what is the number of turns? N is the number of turns per unit length, and we know the length of this small strip or the small element is how much? Dx. So for 1 centimeter length, for unit length, the number of turn is n. So for length of dx, the number of turn will be n into dx. So this is the number of turns of this small element of the solenoid, which is also carrying a current. And we know each turn carries a current of how much? I. So therefore, current flowing through the element. Current flowing through the element will be equal to number of turns into, through its turn, the amount of current is I. So the current flowing through the element will be equal to I into N dx. Let us say that this current is I this. That means the small current which is flowing through the small element is this I this, is written as I this. Okay. Now we need to find, now you see, this small element which is carrying a current of this much I this is behaving like a circular loop, and the point P being lying somewhere at the axis of the circular loop. So point P with respect to this element is lying on the axis of this small circular loop which carries a current of how much? I this. So according to formula that we have already done, if dB is the magnetic intensity at point P, dB is the magnetic field at point P due to this small current carrying loop which is circular in form, then there was a formula, and the formula was mu naught I a square divided by 2 x square plus a square to the power 3 by 2, that we have already derived in the previous chapter. And this equation shows that the magnetic field at any point on the axis of a circular current carrying loop is always given by this formula, where I is the current flowing through the loop, A is the radius of the loop. Remember, A is the what? Radius of the loop. In this case, the radius is how much? R. Because the whole solenoid is having a radius R. This loop will also have a radius equal to R. And x is the distance of that point at which we are finding the magnetic intensity from the loop. So here in this case, from the loop, the distance of the point P is how much? Let us consider from the center, the distance of the element is suppose x. From the center of the solenoid, the distance of the loop that we have considered is suppose x. So this much distance will be how much? R minus x. So the point P is at a distance of R minus x from the loop, or from the small element which carries a current of how much? I dash. Therefore, if dB is the magnetic field at point P, due to the current carrying circular loop, So what you can do, therefore dB according to that formula will be equal to mu naught into I. Here it will be I dash. because in this loop the amount of current flowing is I dash. So I dash, and the radius of our loop is r square divided by distance of the point P from the loop is r minus x. So in place of x, you have to write r minus x whole square plus radius square. Oh, sorry, our radius is small r square to the power 3 by 2. So this is the magnetic field at point P only due to this circular loop, which carries a current of I dash. And according to this formula, the magnetic field at point P will be given by this relation. Okay? Now, but you are actually required to find out the magnetic field at point P due to the whole solenoid. We had just determined magnetic field at point P due to this small loop only. But we have to find out the net magnetic field at point P due to the whole solenoid. For that, definitely you have to do integration. So therefore, the net magnetic. So before that, you do one thing. In place of I dash, you can put this value. So in this equation, you put the value of I dash. So dB will be equal to mu naught into I dash. I dash is equal to I n dx into r square divided by 2. So r minus x whole square plus r square to the power 3 by 2. Now for simplicity, you do one thing. You do one thing that you consider the point P is at a very far away distance. It is at a very large distance from the center. Okay? In order to make this equation simple, what you have to do, you just need to consider the point P is lying somewhere at a very far distance from the center. So if that happens, we can consider that if point P is at a far distance, from the center O. From the center O. So in that case, you can consider, that means what? The distance r is very, very large, or large in comparison to, so this, you do one thing, you put this as A. You take the radius as A because this is already has been considered as r. So you take radius as r, A only. So what will happen? So it will be here A square. Again, it will be here A square, A square, A square. You are taking this radius as A because this distance has already been considered as r. Okay. So what will happen now? R will be much greater than small a. Also, R is again greater than small x because small x is the distance from the center of this circular loop. So definitely x is very small in comparison to R. If the point P is considered at a far away distance, therefore, so what you can write, R greater than, very greater than x. Also R very, very greater than A. Radius of the solenoid is taken to be very small in comparison to the distance R. So this equation will be now reduced. It will now get reduced to mu naught I into n, then dx into a square. You take a square somewhere here, then you bring dx there. Okay, then you can neglect x and a square. So what will remain? 2 x square, but here to the power 3 by 2. So what will remain? Only r cube will remain. So dB is equal to this much. So this is the magnetic intensity at point P due to this small circular loop. Therefore, the net magnetic field, net magnetic field at point P due to the whole solenoid. So lastly, you have to find out the magnetic field at point P due to the whole solenoid. Definitely to find out that, you have to do integration. You have to do integration of dB from. So you have to now put the limit. So you have to now put the lower limit and the upper limit. So if you put if you take this limit from 0 to r, then you will be getting the solenoid from this point to only this point. 0 to L, because the total length of the solenoid is twice L. From here to here it is L, so from here to here it is L. So if you take the integration from 0 to L, you will be getting only this half of the solenoid. Okay, you will be getting magnetic field at point P due to only this half of the solenoid. But we need to find out the magnetic intensity at point P due to the whole solenoid. Definitely you have to do the integration from minus L to L. So from here to this side it is minus L, and from here to this side you can take this as plus L, because this is the origin considered here. Towards the left you take this as negative, and towards the right you take this as positive. So this is the integrations. So lower limit is minus L and the upper limit is L. So now put the value of dV there. So minus L to L, mu naught I n a square into dx divided by 2r cube. Now you see here, except dx, all the other terms are constant. For this particular solenoid, we know mu naught is always constant, I is the constant current, n is the number of turns per unit length, which is also constant, a is the radius of the solenoid, that was also constant, r, the point P is fixed. So from the center, the distance is also fixed. So here r is again constant. So all the constant will come out. So mu naught I n a square divided by 2r cubed. So inside the integration, it will be only integration of dx. So integration of dx is 2r cube. So integration of dx is x. So upper limit is L, lower limit is minus L. So evaluating this integration, what you will now get? So you will get B is equal to mu naught I n a square by 2r cube into how much? L minus of minus L. So it will be how much? Mu naught I n a square, this one will be equal to twice L by 2r cube. So L minus of minus plus. Okay. Achha, put this as equation number 1. Now you see, if M be the magnetic moment of the solenoid, because the solenoid is now behaving like a magnetic dipole. So for every magnetic dipole there is a term, there is a vector term which is known as magnetic moment or magnetic dipole moment. The magnetic dipole moment of the solenoid is taken to be how much? M. M, magnetic dipole moment, the formula of the magnetic dipole moment M is Ni into A. N is the total number of turn of the solenoid into current passing through the solenoid into area of cross section of the solenoid. So now first you have to find out the total number of turn in the solenoid. We already know that the number of turns per unit length in the solenoid is small m, and the total length of the solenoid is twice m. So what is the total number of turn? So total number of turn in the solenoid will be equal to how much? Twice L into n. For 1 centimeter length, the number of turn is n. So for twice L centimeter length of the solenoid, the total number of turn will be equal to twice L into n. Twice L into n. So into current is how much I for every turn the current flowing is I. The current which is flowing through the solenoid is I. So into area of the cross section. That means this cross section. You have to find out the area of this cross section. The radius of this cross section is how much? A. So it's cos pi a square. Okay, pi square. So you got m this much. So for the time being, you got the value of m to be this much. So therefore, equation number 1. Now you see in equation number 1, you can write this. So therefore, from that equation number 2, put this as 2. From equation number 2, so from equation number 2, you can find out mu naught. Sorry, not mu naught. I n, then a square, I n a square into twice L. So that this will come out to be m by pi. Only pi is remaining. So 2L n I a square. 2L n I a square. So m by pi. So put that in equation number 1. So now equation number 1 will be B is equal to mu naught. Mu naught, this value. This value comes out to be how much? M by pi. So divide by 2r cube. So again simplifying, mu naught by 2r cube into m by pi. So you can write this equation as mu naught by 4 pi. Mu naught by 4 pi into 2m by r cube. So lastly, you got this equation, which represents the magnetic field at point P due to the whole solenoid. And this equation, this term represents the magnetic intensity at any point on the axis due to a bar magnet also. So this term also represents the magnetic intensity at any point on the axis of a bar magnet. So this equation, that is the magnetic field at point P due to a solenoid and the magnetic field at any point on the axis of a bar magnet are exactly equal. So you can say that the magnetic field which is associated with a solenoid and with a bar magnet are almost same. Or we can say that a solenoid behaves, whenever a current is passed through a solenoid, it completely behaves like a bar magnet. So this is our proof that in fact a current carrying solenoid behaves like a bar magnet. Okay, thank you.